Good morning, good afternoon, good evening. My name is Marty Fulton. I'm with the SNIA Solid State Storage Initiative, and I'm very pleased to welcome you to our latest webcast from the initiative on how many IOPS, where users are sharing their storage performance needs. Let's move to the next slide where I'm going to introduce our speakers. Do want to do a couple of housekeeping before that. You'll see that there is a place at the top of your website to ask questions. Please do so throughout the presentation. We'll be recording those questions, and Tom and Jim will be answering them at the end of our webcast. We've left plenty of time for Q&A. Also, we surely want your vote or rating of this webcast. Your rating helps us to plan more webcasts and have content that will be of interest to you as we move through the year. We're planning at least one webcast a month from the SNIA Solid State Storage Initiative. So with that, let me introduce Tom and Jim. Both Tom and Jim are well known in the industry as senior analysts and very involved in solid state, persistent memory, and storage. They're also very active members of the SNIA Solid State Storage Initiative. Tom is president of Coughlin Associates. He's the SNIA Solid State Storage Initiative Education Chair, and he has over 30 years in the data storage industry with white papers, articles, a website, 2 conferences a year on a variety of storage topics. He also consults with high-profile companies and advises them on their storage strategies. Jim Handy is with Objective Analysis and an active participant in the initiative. He's a semiconductor analyst with over 30 years, again, in the electronics industry. He's also held marketing and design positions at market-leading suppliers. Tom and Jim have collaborated on this presentation and also on some collateral that they'll be discussing during the presentation. So with that, let me turn it over to you, Tom. I think you're going to be the one that's going to start.
So I don't see anything on the Bright Talk right now, Marty. Is that true?
It should be on.
It's coming through for me.
It's coming through, Tom.
So,
okay.
So Tom, you can wrestle with that, and I can actually start the presentation if you'd like.
Okay. I started it, and then maybe you could click the slides, Jim.
Yeah, I think I will.
Go ahead, Jim.
So our outline for this presentation. And Tom, actually, you could follow along in PowerPoint if you want to, and then just tell me when to click the slides. But
okay, let's do it that way.
Okay, fine then. So why don't you talk to the outline then?
No problem. So we're on the outline page right now. So the work we're going to be talking about is a number of sources, but one of the big sources of this is a survey that we actually have had continuously running since 2012. And we'll talk a bit about the survey. It's for requirements for storage in terms of IOPS capacity and latencies. And we'll be showing some of the high-level results and comparing them for 2012 and 2016. First of all, what are the primary application distribution, then we'll talk about some of these top-level survey results, IOPS capacity and latency. We'll give some ideas about storage tiers, where that makes sense, how that's done. And then finally, some implications and projections for the future, and finally ending up with Q&A. So let's go to the next slide.
Okay.
So as I mentioned before, the survey is ongoing, and here is a tiny URL link to take the survey if you're interested in still participating. It asks for various questions, very short survey actually. We estimate it takes about 5 minutes to do it. Questions related to input-output operations per second, capacity and latency needs, and then system versus storage, especially on the IOPS side. And also we ask for what is the primary application for the IT people that take the survey. The survey is meant for IT professionals. Some results are in a SNIA SSSI white paper, and I think we'll have a link that will be in the presentation at the end here. And the full report is available for purchase from either Objective Analysis or Coughlin Associates. The full report goes into depth, analyzing and interpreting the results. For instance, looking at cross factorization between the various survey questions, and also looking at the results for particular applications. So that can be purchased online. Let's go to the next slide. So let's talk first about the application distribution, and we'll go to the next slide here, which shows the percentage of participants with different primary applications that these IT professionals said they were involved in a data center. Results from 2012 as well as the 2016 reports are here. You can see the databases predominated in both cases, about in the neighborhood of 40–45%. Online transaction processing was interestingly more significant in 2012 than it was in 2016 among our participants, went from 24 to 16%. Science and engineering type work went down a little bit from 10% to 6%. Cloud storage and services went from 11 to 7%, and video creation and distribution 6%, about the same. And archiving and backup actually increased from 4% to 9%. And the mail server and mail storage ended up being about the same. So these were the primary percentages of the primary applications from the survey. Let's go to the next slide. So let's look at these different primary applications individually. The first one is the databases. Now this was the largest population of the IT professionals that took the survey and said that this is their primary application. Databases involve large data sets. It involves random traffic to access various pieces of information in the database, leads to a high input-output load. And as a consequence of these requirements, especially the random access and high I/O load and value associated with that it was an early solid-state drive and flash memory adopter. And in fact, many of these applications previously used a type of solid-state drive that actually used a DRAM. It had to be powered. It was a volatile memory just in order to get the high speed. And today, especially with the price of solid-state drives, flash memory much better than it was in the past, people might be able to even buy enough flash memory capacity that they can load an entire database on flash memory. So on the right-hand side, we give examples of common databases that are out there: SQL, SAP, Oracle, Mongo, IBM, Cassandra, things of that sort. So let's go to the next slide. Moving into the next application that we looked at here, online transaction processing. This would be, for instance, as you see from the figure at the right, selling things. You need, if you're going to do that accurately, you need to verify rights. You need to do a read back after write to do that verification. And so in a sense, you're doing a double operation here with every transaction. So you have a double I/O load, input-output load. And there's no room for errors. You want to make sure that you're transferring $1 rather than $1 million for a particular transaction. On the other hand, speed is imperative. If it takes too long to do anything, people will just walk away. So by providing the speed to complete transactions, you don't lose customers. The delays will cause you to lose customers. Let's go to the next slide. Another application that the primary application was archiving and backup. In this case, of course, you're either keeping a long-term copy of content, you're keeping essentially an active library, an active archive, or you're backing up content so that you've got data protection services available to you. It may involve snapshots and replication. And both of these require high-speed storage in order to accomplish these tasks. On the other hand, the storage, the actual bulk storage, may get by with a lot lower latency. So it requires fast storage perhaps to do the operation, but then you want to lower the cost of, in many cases, people want to lower the cost of the actual storage. Business continuity places high demands on storage. Business continuity, compliance, things of that sort. And as I mentioned before, a lot of archives are not just something that just sits and provides a long-term copy, but it may be accessed more frequently, leading to some additional latency requirements. And this leads to a concept called active archives. And basically, archives that are active are becoming more commonplace than the passive traditional archives. Let's go to the next slide. This is an increasingly important topic as well. One of the primary applications is cloud services and cloud storage and virtualization. In particular, abstractions such as virtualization can lead to much higher utilization of physical assets, but it leads to very intense input-output operations, so often called an I/O blender. There are many streams. You've got scrambled I/O across many different virtual machines. It can be highly random access. And this is an application where SSDs are actually more popular than hard disk drives for rapid access, or to be able to, at least for a lot of the initiation of these virtual machines in particular. So many virtual machines and virtual desktop systems use flash cache to meet their speed requirements. Let's go to the next slide. Another area that we looked at as one of the primary applications was science and engineering. A lot of this is going to be simulation, maybe complex problems like genome sequencing, computer-aided design, computer-aided manufacturing, natural resource planning, for instance, oil, gas, things of that sort, water, and then nuclear modeling. These oftentimes involve large data sets, or astronomy, all these kind of things involve large data sets. And also, these are a lot of the people involved in this are highly educated, so they tend to get paid a fair amount of money. And so it's expensive talent. As a consequence, you don't want them sitting around waiting. So there are some speed requirements in this application. Let's go to the next slide. Another application that we looked at, and one that I've particularly been doing a lot of work on, is video creation and distribution. These involve large data sets, increasing in size as we end up with more higher resolution, higher frame rates, higher dynamic range, and more cameras being used on projects. So we can have multiple video streams. Randomized access is possible, though some of this is sequential, at least for individual streams. A high bandwidth is required, and again, oftentimes for professional video, it's expensive talent, and again, you don't want them to sit around waiting. So there's some need for performance in these applications. Let's go to the next slide here. So I mentioned I do some work in the storage and media and entertainment. One of the things I do is a report on digital storage and media and entertainment. And from our 2016 report, this is projections looking out in the future, showing different types of revenue by media type. 2015, flash was about 38%, tape about 6%, hard disk drives about 55%, and optical at about 1%. Projection for 2021 was that flash, the actual revenue would be increasing to about 51%, with hard disk drives at 46% and tape at 3%. Now, if we go to the next slide, let's take a look at what's driving those 2021 projections. Again, this is for flash. A lot of it is the acquisition as you get more cameras, higher resolution, higher frame rates, etc. Having storage, rugged storage for professional cameras and other rendering and other types of applications is, we think, going to be the biggest driver. There's great value in doing that. Then post-production, we see flash becoming more important there. And on the delivery side, for instance, in video on demand, flash is also playing a more important role. So let's go to the next slide. We have one last case of these applications we'll talk about, and then Jim's going to be giving you some discussion of the actual data here. And this is the Exchange service. This is tasks such as email, scheduling calendars, general storage of attachments, things of that sort. There can be thousands of users, and it's a fairly chaotic workload that you're working with here. You have multiple mailboxes, asynchronous sends and receives, and also spam and virus filters and these sorts of things. So again, this is a summary of these key applications. And if we move to the next slide, Jim can take over and talk to you about some of our top-level survey results. Take it away, Jim.
So now that Tom has painted the background for us, let's actually look at how people responded to the surveys. And just to reiterate something that Tom said is that we published an original report in 2012 with this information from the survey. At that point, we've had the survey ongoing, and so because of that, we've been able to get information from 2016 and compare it to 2012. So the following slides are going to be comparing what we learned in 2012 against what we learned in 2016. So one of our questions, Tom went over what the dominant applications were, the high-speed application that people needed to get high IOPS for. And we asked them what their IOPS requirements were. We asked this question as a multiple choice question and had it in orders of magnitude in order to keep the survey from getting too large. One of the things that we had to do was to encourage people to actually fill out the form. And so we promised them that they'd take only 5 minutes to fill it out. That means that we don't have a whole lot of resolution in it, but we have enough to really draw some conclusions. The light blue columns in this represent what our 2012 survey results were. And the dark blue in this and also in following slides will represent what the 2016 survey showed us. And you'll see that we have for IOPS requirements something that's pretty much a bell curve for how the respondents answered, with a little bit of a shift over to the higher IOPS area for the 2016 survey from where we were with the 2012 survey. If you take an average of all of that, you find that there was a 37% increase in the median IOPS required, but it was still a very broad range. You've got 100 IOPS by some respondents, and that represents what you can do with a hard disk drive. And then as you get up into the thousands and hundreds of thousands, then it comes to SSD speeds. The million and 10 million IOPS, we looked at those, and we looked at some other aggressive inputs that we got from some of our respondents, and we were forced to wonder what would have happened if we had put in a question that said, well, how much are you willing to pay for something like this? Because we think that, there were probably some blue sky responses that we got there that said, well, if it all costs the same, then I'm going to ask for 10 million IOPS. But still, you'll find with this and with some of the other ones that there were a lot of people who gave us very reasoned answers, and this 100K IOPS, you can see that, that's still a large share of the respondents, and we have got respondents who have shifted their needs so that we've got, lower needs in the lower IOPS and higher needs in the higher ones. So there is a migration going on to take advantage of the improvements that are being made in SSDs. For the capacity required, we also asked how much capacity do you need, and we didn't go orders of magnitude in this. We had half steps in between. So we went from 50 gigabytes to 100 gigabytes, 500 gigabytes. And you can see that that's a much flatter distribution. It's not as peaky in the middle as the IOPS requirement. This is that we did have a wide range of applications, and so because of that, we also had a wide need for different amounts of capacity for this high-speed storage. But still, disk drives have gotten considerably higher in capacity since the 2012 survey, and SSDs have also grown in capacity according to Moore's law. And so it's not at all surprising to find that the respondents to the survey, on average, said that their mean capacity increased, their needs increased by 17%. Something that I should say here, too, is that all of these measurements that we have were measured for each application. So the respondents chose an application, like Tom showed you early on in the presentation, and we have capacity requirements and we have IOPS requirements by application broken out in the report. The SNIA white paper gives these, top level for all applications figures, but if you really want to dig into it, then the report has, I think it's, over 150 different charts that compare all of these things against each other. So we got a lot of resolution in this. We also asked how fast could your SSD be before some other bottleneck got in the way, and that's what's shown on this next slide. And that's something else that increased. What that indicates is that the servers and the networks that are being used by these survey respondents have improved over time. And that's something that drives the need for higher IOPS from the SSDs. We saw a 36% increase in the speed, the maximum speed SSD that could be used by the system before some other bottleneck got in the way. you know, and this is a narrower distribution, once again, like the IOPS requirement distribution. So it shows that there's a lot more focus on the speed than there is on the capacity here. Something else that we did with this data was we said, okay, well, you know, we have these numbers showing the IOPS and showing, you know, how much capacity is needed, that kind of stuff. What if we cross that information with each other? Oh, I'm sorry, I'm getting ahead of myself. I missed a slide here. So I'll talk
Don't
about
forget
that
latency.
yeah, fastest latency in the system. So this, you know, IOPS is good, and IOPS is the center of attention for an awful lot of storage. But for a number of applications, if you have high IOPS but you've got not so good latency, you're going to be in a lot of trouble. And so we asked, what is the fastest latency that the system can use? And got responses, you know, 10 milliseconds is typical for network-attached storage latencies, and so it's not at all a surprise to see that there was a big peak in 2012 for 10 millisecond latencies, that people didn't anticipate being able to use latencies that were faster than that unless they wanted to go with direct attached storage. That has changed over time, and now users of all-flash arrays or users who have decided to pull storage back into the server have decided that they want to have faster latencies than that. And so we actually saw the biggest change being the decrease in mean latency between 2012 and 2016. And that really comes shining through in this chart, that there's a big shift in latency requirements. People are really getting their arms around what Flash can do, and they're learning how to manage it so that they can get it. So as I was saying before, prematurely, you know, we have all of these statistics. What can we learn by plotting them against each other? And so the scatter chart in the next slide is actually one attempt to do that. In this one, we've got the IOPS measurement across the bottom, and we've got the latency requirements running up the vertical axis. So what this does show is it shows where we had answers where people needed fast latency and very high IOPS, which would be the lower right-hand corner of the slide. And then we had respondents who didn't need that many IOPS, so that would move them toward the center of the slide and could deal with a long latency, and so that moves them further up on the vertical axis. You can see there's a pretty broad distribution, but if you really think about it, there is a little bit of a slanting down to the right kind of a shape to this configuration. Something that would have shown up more in this is if we showed larger or smaller dots for the number of respondents who filled in each one of these areas. Unfortunately, our graphing software limitations kind of got in the way of that. But one thing that we were able to do was just to kind of compare things to the real world. We put on this column on the left-hand side that showed roughly where each technology would fit in. So you can see the slowest latency at the top is network storage, a SAN. And then below that we have hard disk drive. And then below that, the faster latency is SSDs. And then we get down to DRAM speeds and on CPU cache. It was a little bit surprising to us that we got as many respondents as we did that said that they'd like to see their storage be at DRAM speeds or even at cache speeds. But, you know, once again, we've got this issue that we didn't really tie in what the cost would be to the system if they were to get that. And I think that you would have gotten some pushback if we had said, well, yeah, you can have that, but it's going to cost more than 10 servers by themselves cost. So, you know, we did have some people who were probably taking some liberties with this, but for the most part, the people who responded in the SSD, HDD, and SAN areas gave us some information that actually can be actionable. And once again, we have these charts, and we have ones that have IOPS versus capacity and latency versus capacity and that kind of information. They are all provided by application in the report. So, you know, it gives information that would be, for example, database specific which this top-level information doesn't do. We end up having to do a several hours-long presentation if we were trying to present all of that in this webinar, and we certainly don't want to do that. And so the next section is about developing storage tiers, and this is where I turn it back over to Tom. He's going to be describing the slides that are there. And Tom, do you still need for me to flip the slides?
I do indeed, yes.
Okay, so fine. So we're going from
Much
22, good. The outline slide, over to 23.
Yep. So this actually is from some work that I did with Steve Hetzler, who's a fellow at IBM. And he developed this concept of what's called the touch rate. And that is, if I have a storage device, hard disk drive, SSD, for example, or tape, then there's a rate at which I can touch any of the content on the device. I can, for instance, write or read it, for example, over a given period of time. And so we're calling that the touch rate. And on the vertical axis in this chart, we're plotting in a log scale, a factor of 10 with every major increment, the touch rate per year, how many times you could touch all the data on the device in 1 year's time. On the horizontal axis, we're plotting the response time. So that's, again, in log scale with shorter times going to the right. And this is looking at how quickly, once you give a command, that command can be completed, and then it's ready to do another command. For instance, I'm writing or reading. So we're looking at the amount of time I can do something on all of the data that's stored, all the data that's on the device, all the possible places where bits can be stored on the device over a given period of time, versus how fast I can address the data on the device to complete a command within a period of time versus in seconds. So what we can see here then is we can create sort of operation tiers where we start in the upper right-hand side, where it's a very high IOPS. I have very fast response times, far right, and also I can touch all the data on the device in many times over a year's time here. So that's that upper right-hand side. Follow that by moving to the left and downward, a transactional approach, the transactional area, followed by nearline, and then something we're calling semi-active and cold active, again moving down to the lower left, and then finally inactive. So as we go along the vertical axis, we have more accessibility to the data in the device. As we move to the right, it gets faster, we have higher performance. Now, we'd all love to be in the high IOPS region. The problem is that you go from the lower left to the upper right, the raw storage capacity tends to increase. I'm sorry, the raw price per storage capacity tends to increase. So there may be places where spending the money and moving in the far right makes sense. There may be other areas where I'm willing to make some trade-offs, and that leads to this concept of tiering. In fact, if we go to the next slide, we can see now overlaid on that prior chart of the touch rate versus response time, characteristics of different types of storage devices. Flash memory is at the far right there, going into the high IOPS and transactional mode. And by the way, the place where you tend to operate these devices is going to be at the knee of the curve. That's where you get the best trade-off in terms of the performance and the accessibility. So that you tend to work in that area there. So you can see the range of where flash memory device is going to be operating. Then 10,000, 15,000 RPM performance hard disk drives, and then lower RPM capacity hard disk drives will move down, to the left and down. And then, for instance, technologies like tape is in that inactive region there. So the capacity hard drives are in this, tend to operate in this nearline, semi-active region. The performance hard disk drives can work in this transactional region, and if you want higher performance, that's the flash. So these are the different, this is characterizing some of these technology things, an interesting way of visualizing this. Now, if we move to the next slide, now we can use these touch rate versus response time charts. We can actually plot device performance on here. So we're showing, for instance, a PCIe or NVMe flash memory device in the upper right-hand side there. So we're showing, again, the touch rate as a function of response time. for different sized blocks of data that are being moved around. And then to the lower left, that's the red line. Then to the lower left, we're showing a hard disk drive, again, with different sized blocks that are moving, and that causes us to move on that curve. And as I said before, you tend to want to work in the knee of the curve for each one of these technologies. Now what that means then, if I want to create a tiered system with hard disk drive and flash and moving data as is needed for more quick access to the flash and then back to hard disk drive when it's not, I'm kind of guided, kind of controlled in that transfer by the slowest technology. But you can see if I get 1 megabyte objects that are moving around, that I can see where the size of the objects I'm working with, the transfer in the objects. So it's an interesting way of looking at this. If you're interested in getting further information on this approach, there actually is a white paper that Steve Hetzer and I did about a year and a half ago, and we'll show a link at the end here where you can find a copy of that. And I think we'll turn this back over to Jim, who's going to talk a bit more about some of these storage tiering considerations.
Yes, and I'm showing a slide now that's got a heart on it, but that doesn't mean it's a Valentine for our audience. Jim Pappas, many of you may have seen him make his presentation at some SNIA event or another. He about 2 years ago started talking about how to envision speeds of different levels of the memory storage hierarchy. And, you know, you could compare this to latency. And he says, okay, if a DRAM access from the CPU is a single heartbeat, well, an SSD access is about 1,000 times the latency of the DRAM, and so that would be about 1,000 heartbeats. And what can you do in the time that it takes for your heart to beat 1,000 times? You can walk about a mile. So, you know, that's a reasonable thing. You also look at that and you say, okay, well, then that means that if you could grab something off your desk in the time that it took for your heart to beat once, or you could walk a mile to go and get it, which one of those would be a more efficient use of your time? And under what cases would you be willing to have something a mile's walk away versus right available where you could get it? And, you know, that same kind of thinking would go into where you put things in storage. So how does hard drive compare to this? Well, a hard drive is about 1,000 times the latency of an SSD, or it's about 1,000,000 times the latency of DRAM. And what can you do in 1,000,000 heartbeats? Well, that would be about the amount of time that it would take for you to ride a bicycle from San Francisco to Miami. So, you know, that really puts things in perspective, is that if you've got something that has high-speed needs, you certainly don't want to have it out in Miami. But, you know, you probably can't afford to have everything that you want in DRAM, and so an SSD is a good place to put it in between. So I think that's a really good analogy. We decided that we just include that in here because of that. So how does DRAM and hard drive compare against each other? And Tom and I put this together for a SNIA white paper and a report called Hard Drives and Flash Memory, A Marriage of Convenience. This was some time ago, and so you see this data only goes out to 2011 with DDR3. But what we compared was the speed of DRAMs, which is constantly increasing with all of these DDR interfaces, against the speed of hard drives, which have been on a much slower track. And if you look on the left-hand side of this in 1995, then a DRAM may have only been about 200 times as fast as a hard drive. And you get up to 2011, you see that it is pretty steadily increased up to the point where it's now about 6,000 times the speed of a hard drive. That continues to increase, and the fact that we have these newer SATA 3 and other high-speed interfaces doesn't really change the access speed of the hard drive. It just changes the ability to empty out the contents of the DRAM cache to the system. And so because of that, I'm sure that you could probably draw roughly a straight line continuing on this curve out there. We just haven't updated this chart since that time. So, you know, that underscores the speed difference, as in the last slide, between DRAM and a hard disk drive. So I tried some years ago to put that all in perspective in a way that was really easy to understand. So this is a log chart again, and you know, the charts that Tom showed just before had log charts. I hope that people are comfortable with this as we are. But this one shows price per gigabyte and just a rough approximation across the bottom, and then the bandwidth for various technologies running up the vertical axis. A sales guy that I've worked with calls this the plaid chart because of the way that it looks. In the upper right-hand side, you've got three orbs that roughly represent the different levels of cache inside the processor, L1, L2, and L3 cache. Each of these, as it goes up, gets higher bandwidth, and it goes further to the right, it gets more expensive. So you've got this memory storage hierarchy where every orb, if it's on the right, is more expensive than the one just below it, and if it's higher up, then it's faster than the one just below it. And they all fit nice and tidily in here. You can see that DRAM fits just past the caches. It's cheaper than the cheapest cache. It's slower than the slowest cache. But there was this gap developing between DRAM and hard drive because of the phenomenon that I showed on that prior chart. And so this is where a NAND flash in the form of SSDs ended up finding a very agreeable place in the system, is that the flash doesn't replace the hard drive because hard drive is still significantly cheaper, but it is faster than the hard drive. And NAND also can't replace DRAM because it's slower than the DRAM, but it's significantly cheaper than the DRAM. NAND flash today costs about 1/15 the cost of DRAM, and that has been increasing over time. Tape also fits into this hierarchy, that there are certain things that you're going to want to store in tape because of the fact that it's significantly less expensive than a hard drive, and that it's going to be much slower. And I'm not saying that all systems are going to use every single one of these orbs. These are just all of the orbs that exist in the system. But what this does show is, why we've had SSDs really pop onto the scene. NAND flash wasn't cheaper than DRAM until 2004, and it was very shortly after that that SSDs started becoming popular. And so it's now a more permanent it plays a more permanent role in the system, and it can do an awful lot to improve system performance. And as a matter of fact, I've run into a large number of enterprise system administrators and hyperscalers who they view NAND flash in the form of an SSD as being a way that they can reduce the amount of DRAM that they use in the system, because the DRAM was actually storing copies of what was on the hard drive, and the larger it was, then the fewer times you'd have to take a bike ride to Miami. But, now that you've got NAND flash in there, then you've got it a whole lot faster at a reasonable cost. And so what that means is you don't have to keep bulking up the DRAM to make up for slow storage. You now have NAND flash for that. Moving to the next slide, these are actual costs of NAND flash and hard disk drive over time. And this kind of illustrates what was going on in that prior slide, is that we didn't have flash taking the place of hard drives. And the reason why is because these two are on roughly parallel price reduction curves. And the bumps in these curves depend on things like shortages and oversupplies. But basically their cost to produce are going down at a steady rate. This is a semi-logarithmic chart. You can see that the dollars per gigabyte on the vertical axis is in orders of magnitude. And one of the magical things about the semi-logarithmic chart is that if you've got constant growth, then it shows up as a straight line on the chart. Whereas if you were to show it on a standard non-semi-logarithmic chart, one that had a linear vertical axis, then you'd end up with these hockey stick curves. The separation between hard drive and flash would seem to disappear on a chart that was not semi-logarithmic, whereas you can see here there's a very real 10-to-1 or so difference. It was a little bit larger early on, but it isn't disappearing anytime really soon. These curves both go down by mechanisms that are very similar. The flash curve is going down based on Moore's law, which says that the number of transistors on a chip is going to double every year or two. And the hard drive is driven by I think it's Insight's hard drive target that is set by a consortium of hard drive manufacturers, where they aim to increase the capacity of a hard drive by 30% every year. Well, that 30% per year of hard drive capacity increase actually very closely matches what's going on with Moore's law. And as long as these two phenomena are driving the costs of these two media, then we don't expect to see any kind of a crossover between hard drives and flash. And we should expect to see flash continue on as a faster version of storage that commands a premium, and that hard drive will be the cheaper version of storage that might be a little bit slower than flash. Regarding IOPS, we wanted to see, how price and IOPS tied into each other. And so this was just a very simple exercise where we took a number of different SSDs and hard disk drives and took their IOPS ratings and plotted them on this horizontal axis. And then we plotted what their price per gigabyte was on the vertical axis. And this was something we did in 2012. We didn't put in the time to update it for the 2016 data, because we thought that the point that we were showing was probably clear enough, is that there is, for most of these, a pretty good relationship between what IOPS you ask for and how much you're going to pay in price per gigabyte, that it goes up and to the right, and most things stay within this orb. You've got outliers, of course. You've got the very slow hard disk drives that command a very low price that kind of fall out of the orb, and that could be that people are just trying to do some kind of a fire sale and get rid of things. And then you've got some manufacturer who's got a not-so-high IOPS device that they're selling for about $100 a gigabyte, and if they can find people who will spend that kind of money on it, then, by all means they should. But for the most part, you'll see that there is a kind of a rule here that the amount of IOPS that you get, it depends on how much you're willing to pay for things. And, once again, this would have been a great thing if we had found a way to figure that into our survey and make people actually honestly answer according to what their budget was. But, because of the fact we were keeping a 5-minute survey, there are a lot of things we could have done, but we would have ended up extending the time on it. We thought we got more value by having more people respond to the survey than by actually asking them questions that would make them worry and think about things before answering them. So where do you get these kinds of IOPS? This is just kind of a graphical way of looking at what gives you different levels of IOPS. So a hard disk drive will give you hundreds of IOPS. And so we've got it on the blue side of this temperature chart here, 10 to the 2 IOPS. As you go up to SATA or SAS SSDs, you will get somewhere in the thousands to tens of thousands of IOPS. And then as you move up to PCI NVMe SSDs, then you very easily will get tens of thousands, hundreds of thousands, to close to 1 million IOPS. There's some very high performance NVMe SSDs. But what about those people who needed DRAM speeds? There are modules that get those to them, and these all pretty much have to be put onto the memory channel, onto the DRAM bus, and communicate by these very high-speed protocols, DDR3 or DDR4. SNIA is actually spending an awful lot of time and effort defining how these new memory channel storage areas or devices are going to be used, what the communication protocols are for them, and how to address them through software. And it seems like the organizations are making great strides in that. But this one that I show here is that's NVDIMM-N. It's actually DRAM that has NAND flash to store its contents should the power disappear. And that little wire that you see going off the back, that's for a power source, that when the power disappears, that power source keeps the DRAM alive until it's been able to shuffle its entire contents off to the NAND flash. This is providing new ways of looking at how computing is done as a whole. And we're expecting over the course of time for people to be designing an awful lot of this into systems and developing software around it to the point where probably 10 years from now people will be saying, we don't know how we got by without it. And so now we move over to what are the implications and projections that we can draw from all of this data that we got from our survey. We found that users who responded to our survey need two things. They need IOPS and an increasing number of IOPS, as we showed between the 2012 and 2016 numbers, and they need increasing capacity. Those are the increases they need, but they also need decreasing latencies. And so everything needs to continue to get better. But this is technology that happens. We need to, the users needed or indicated that they're adopting SSDs in larger quantities, mostly to be able to achieve these higher IOPS. But they're not abandoning hard disk drives. Hard drives are very useful for filling a tier behind SSDs. In certain systems, then you're not going to find this happening, but for most of the more complex systems, hard drives are here to stay and will continue to be used behind SSDs as a slower, cheaper form of storage. We did find that there were bottlenecks in other parts of the system, but those bottlenecks, too, were moving up to faster speeds, and those bottlenecks were the network, software, and the servers themselves. But there's a growing focus on IOPS, that more people are understanding what it means, and that means that both SSDs and hard drives are going to be able to experience some growth. All of this is in a report. This is just a little plug for it, and anybody who wants to download the slideshow can get to the hot links in here, but basically if you go to Objective Analysis or to tomcoughlin.com, both of these will give you an opportunity to have a look at the outline of the report, and you can, we'd be much obliged if you were to find an interest in it. And so with that, we're going to ask you to ask your questions. I see that we've got some already, and this is something that you can ask your questions now on the website, or if you're listening to the pre-recorded version of this at some later date, then you can send questions to this email, askssi@snia.org. And we will, get those questions turned around to you very quickly. So let me just see. I need to click on the questions. Okay, so Tom, you can't see the questions, can you?
I cannot see the questions.
Okay, fine then. I'm just going to start at the top. So, actually, I should start at the bottom because that's the one that was posted first. So let's see. Okay, I got one that's, can you tell me the link? I'm going to ask the respondent to, or the person who asked the question to ask a question that's a little bit clearer because I'm not too sure what link you're asking for. There was one that says no virtualization represented in the survey. Tom actually spoke about virtualization. Perhaps the person who asked this question came in late, but there was that slide that had the blender on it. I can actually pull that up again. Just a moment. Sorry, it takes a second for this thing to load. It's taking longer than I was expecting. So, okay. So there's this slide about the I/O blender that Tom talked about, and virtualization was very well represented in our survey. we ended up with a number of respondents that said that this was an issue for them, and we had the statistics broken down according to, that we have responses from our survey members that say this is the number of IOPS that we need in a virtualized system and that kind of thing. So that is very well represented in the survey.
So it might be that question on the link was the link to the presentation afterwards. Probably Marty can tell a little bit about that.
Okay. Yeah, and there is a link to the presentation. Yeah, I'll take it back to the slide that has the links. So
if you go to the last slide, there's a link.
It is. I'm just pulling up that thing that shows all of the slides at once, and it seems like it's taking longer than I thought it would.
Oh.
Okay, last slide, not the last slide. The next to the last slide.
To download this webcast, there is.
Yeah,
the very last.
Yeah, that shows the source material. There's an IOPS white paper. Oh, okay, I see. So that's the link that.
There's one more.
Marty.
Yeah, I think maybe that's what they're asking for. We didn't show that yet, so.
Oh, okay, fine then. Yeah, so this is where you can download the webcast.
And listen to it at your leisure.
Okay, pull down to the lower level of the questions again. Okay, one of them is just a comment saying, I would separate out cloud storage and some virtualization. And we might do that for future versions of the survey. At the time that we put it together, it seemed like that was a good level of them to put together.
Remember the original organization, this was back in 2012. So.
Yeah. Okay, the next question we had is, are the required IOPS at 4K block size? And that was the way that we defined it in the survey, that we said how many random 4K IOPS do you need for your most critical application? So that was in there. Okay, another question. Are the IOPS required for your dominant application on a per-device basis, or per server, or per CPU, or per what? We didn't specify that, and what we assumed the respondents would answer was what they needed for that application by itself. So if it was a system that needed a SAN, then they would be specifying it for the SAN. If it was a system that needed it as direct attached storage, then they would be specifying it for that. But we didn't break it out to that. Once again, we were trying to keep the survey down to 5 minutes, and so we didn't get into an awful lot of small details about what was in there. Now, I realize that if this is somebody who's supporting, if the question is being asked by somebody
Jim,
who is a supplier.
I think you're breaking up a little bit, Jim. Can you move closer to your phone or move your phone a little bit? Because I think you're breaking up a little bit.
Okay, maybe Tom could address this question. Are the IOPS
what was the question?
Now you're better.
Oh, okay, fine. And I don't know what happened there. Okay, so are the IOPS required for the dominant application on a per-device basis, per server, per CPU, or what?
Let's see. So it was on it's on the application basis is what we were asking about. So it's probably going to be the whole system performance that they're looking at. But again, we were trying to break that down into the different types of storage technologies. In terms of the requirements for storage, so it's a storage system requirement that we're looking at that we were trying to address. I hope that answers that question.
Okay. The next one is a comment. It says 17% capacity increase over 4 years is much less than Moore's Law. And I have to agree with that. I'm not sure what to attribute that to, but I would guess that users are becoming more sophisticated and using maybe more careful judgment as to how much solid-state storage they're putting into their systems in order to get the best bang for the buck.
And there's some applications where you can get, for instance, if you store your metadata on a flash memory, it may give you, for instance, searching applications give you much faster access to the content. So there's certain things you can do that provide a very real and immediate boost in performance at some minimal cost. And there's other applications where, you know, the speed is worth the money, and therefore you will pay the extra money to get it. And as the price of flash goes down, there may be more applications where people will do that.
The next question is, will the content, including the results, be shared? And there is a SNIA white paper that is on that next to the last slide that you can download that. That's got the graphics that were used in this presentation, or at least the ones that were from the survey, along with an explanation of how they all work. So, you know, that's something that's readily available from SNIA. But Marty, too, were you going to make the slides available separate from the presentation, or is it just the recording of the presentation that you're going to make available?
Thank you, Jim. Typically, we upload the slides to the website. So if you go to the SNIA website, or you can send an email to asksssi@snia.org, and we can make a copy available to you. Typically, we put them up on the white paper and collateral page of SNIA. So we'll do that as well. And I just want to put in a quick plug, since we only have about 4 minutes left. Please rate the survey. There's a button that says rate this at the bottom of your presentation. We really appreciate your rating and your comments. And then the other thing I want to say is the questions, if we don't get to your question today, we will have a follow-up blog posting that we will answer these questions. Probably within the next month, we'll have a blog that will cover some of the answers to these questions that we don't get to today. Back to you, Jim.
Okay, fine. And the next question was, how do you see Intel Optane impacting storage? That chart, I'm not going to try pulling up the slide because it's been taking so long for me to do that, but that one chart that I had that I jokingly called the plaid chart, it had a series of orbs representing tape, hard drive, SSDs, DRAM, and then the 3 levels of cache in the processor. Optane is just another orb that fits in there. It fits in between DRAM and the NAND flash. And so what I would expect to see happen is the same way that NAND flash has served to reduce DRAM needs in systems, I would expect to see Optane also reduce DRAM needs in systems, but also to improve the performance and give more performance per dollar, more bang for the buck for these systems. So Objective Analysis wrote a report on that back in the end of 2015, and I think with the exception of the fact that Optane's about a year late from what we're expecting to see there, that our findings are still very much the same, that it has the possibility to become a really major market, and it makes a lot of sense from a technology standpoint. The next question is, what do you think about ultra-high capacity SSDs? And I've been taking over most of the questions. Tom, do you want to say what you think about ultra-high capacity SSDs?
Someday they will be affordable. The very high capacity SSDs, for instance, at the Flash Memory Summit last year, there was one company introduced a 60 terabyte SSD, and another company introduced a 32 terabyte SSD. It seems that both of these were more concepts that, yes, we can fit enough chips to give you that capacity in a box of a certain size, but not actual products. So the highest capacities available now tend to be in the sub-10 terabyte range for the most part. The actual available, there may be some that are higher, but you know, most of the higher capacity SSDs right now are in the sub-terabyte range. Again, with some, and that'll be increasing in capacity with time, you know, in terms of the bulk of those higher capacity SSDs. And it's driven by the cost and performance versus the storage capacity that you're getting too. So, you know, so those are requirements, and that's kind of where I see things right at the moment.
Okay, the next question is, what are your actual numbers in pricing comparing SSDs to hard drives? Is it still eightfold? And yeah, Tom and I just put those numbers together recently for that chart. We're still seeing a pretty big gap between the two of them, and what we're comparing is inexpensive solid-state drives against inexpensive hard drives. when you're trying to compare higher performance solid state drives against anything, then the price goes up significantly. And likewise, if you're trying to compare higher performance hard drives against anything, the price goes up dramatically, and then you end up with kind of confused numbers. So we find that it's easiest to take the least expensive things and compare them against each other.
So, to answer the question directly, it appears that we still have the going down seemingly in parallel, for under those considerations, the lowest cost of these, and not the lowest, but the lowest useful cost of these products. You can buy very cheap flash, probably the falls even lower than this, but you may not want to use it for an IT application. The numbers here now are in the range of about a 5x difference in cost between them on a dollar per gigabyte or terabyte basis.
So Jim and Tom, we probably have time for one more question. We're really at the top of the hour, so
okay.
I don't want you to cut off in midstream, so we may want to stop now and or just take one more.
Okay, why don't we just do one more? And well, here's a good one. Will the price gap between SSDs and hard drives ever cross in favor of SSDs? And we don't see that happening. As long as hard drives are increasing in capacity by 30% per year, and Moore's law is causing flash prices to drop by about 30% per year, then these two should stay on parallel tracks. But that doesn't talk to the total cost of ownership, which there are a number of people who, from their perspective, find that flash can save money over hard drives when you look at the entire life of the product. So, Marty, do you want to close up?
Sure. So just want to thank everyone again for attending our webcast. As I mentioned earlier, we will have a blog posting on our SNIA solid state blog within 30 days with answering some questions that we didn't get to today. Please rate the session, and we'll look forward to seeing you next time. Thanks again to Tom and Jim for a really informative presentation. Good ratings, and maybe we can do a 2020 how many IOPS. What do you think?
I like that. Thanks very much. Thank everybody for listening.
You. Okay. Bye-bye.
Thanks.